Hello to everyone who's joining us from every part of the world. This is indvideotech. We represent video technology in India. We have monthly meetups. Feel free to join us and contribute. We have two speakers lined up today, Fabio from Vinova and Saravanan from Bitmovin. So Fabio goes first. I'll hand over the floor to him.
Thank you very much. Thank you, Krishna. Hello, everybody. And well, thank you for having me in this session. I will kind of take the next 20 minutes of your time to kind of walk you through MPEG5 Part2 LCEVC. So one of the new compression standards that are being ratified within MPEG. So I will talk a little bit about what is MPEG5 LCEVC, why is it different, and how you can get access and test it today. So, very brief introduction. I mean, video is everywhere. We know it. Different requirements for different applications, but really it's kind of number of frames, the size of frames, the number of bits being thrown around the internet and various IP networks is, for the large majority, video, and therefore this makes the issue of optimizing this video delivery as much as possible a very real and tangible one, and one that can have effect at the bottom line of many different organizations and companies. So compression standards have largely addressed this over the years. Compression standards have been around for a while. Have affected our lives already, from the digitization of television to internet streaming, telepresence, of course we're using it today during the sessions, mobile video communication, and much more. Video standards have been essential to kind of determine interoperability between different systems, encoding system and devices in consumer hands. And in order to make these as cheap as possible, they had to be kind of like, the specification had to be frozen, right? It had to be frozen, hardened in silicon, and made available to all of the devices in people's houses or hands. However, the process takes time. So it's about 7 to 10 years it takes to go from one standard to the next, typically. And it takes time for that standard, once ratified, to find its place in the market. It has to be hardened in silicon, 2 to 3 years, and then the devices have to reach a critical mass such that a service can address them cost effectively. To the point that, the most ubiquitous standard today, H.264 HEVC, it's a good 17 years old, and still, the most used. However, new standards have followed. HEVC is growing in popularity, but new standards are coming from MPEG. Namely, 3 different standards are going to be ratified this year. I will cover a little bit of the status of this, but both EVC, Essential Video Coding, and BVC, Versatile Video Coding, are currently at FDIS, Final Draft International Standard. And LCEVC, or Low Complexity Enhancement Video Coding, is currently in ballot with the ISO organizations around the world. So today, I will want to specifically kind of zoom in and focus on LCEVC, because LCEVC is different. It's not like any of the other standards that came before it. So why is it different? So while the majority of MPEG standards have been evolutions of a previous generation, MPEG5 LCEVC is a new approach. It's different. It's not a standalone codec, but an enhancement for all other codecs. And all other codecs could be MPEG codecs of the past, like MPEG2, HEVC, HEVC, or MPEG codec of the futures, like EVC and VVC. But not only, and this is an interesting thing, is MPEG5 LCEVC can be an enhancement for non-MPEG standards. So it does, it can be applied to codecs like VP8, VP9, and AV1, for example, which are non-MPEG standards. Okay. Why do we need an approach like LCEVC? Well, the reason is in the name, low complexity enhancement. So LCEVC acts upon two different dimensions. One is that of the compression efficiency of a given codec. The other one is that of the computational intensity, if you want, the requirements of a given codec. So we know that over the years, generations of compression standards have improved the compression performance, reducing the bitrate requirements, i.e. the bandwidth required by a given, to achieve a given quality, or the file size of, of a file of a certain quality, while at the same time needing more computational power to use the increasingly expanding tools that that the standard was making available to the encoder. So roughly, the bandwidth requirement have largely halved over the course of the different generations, while computational requirements have multiplied by orders of magnitude, to the point that VVC today is about 10x the computational intensity of HEVC, which itself was a 3-4x versus AVC, and so forth. So LCEVC, as I said, is applicable to across the spectrum of codec, and kind of redefines the trade-off between the computational requirements and the compression efficiency of a codec. So it affects both dimensions and improves the compression efficiency of a given codec, which I will call the base codec, the codec that it enhances, while improving its computational efficiency as well. And I will explain how. But this again is a paradigm shifting in the approach, right? So it is low complexity in the sense that it's an enhancement that is kind of deployable via software with very little power consumption addition, if you want. And it improves the compression efficiency of a given codec. Okay, so before I go into how is this possible, what is the magic sauce that makes LCEVC effective on both of these dimensions, I want to stress the fact, perhaps with, pardon the poetic analogy, with the difference between LCEVC and the other codecs, right? So if you want to think about it, other codecs are like stars. They're bright, they're very effective in their luminosity, but their light takes years to get to us because we have to deploy them. They have to get into devices, into silicon first, and into devices. LCEVC is a completely different approach. It's a completely different celestial body, if you want. It's more like the moon, right? It needs a star to be bright, right? But its light takes 1.3 seconds to get to Earth, and it's quite bright. Okay, so just perhaps to more vividly register the difference between the two different approaches. So again, the LCEVC is a unique value proposition because it's the first MPEG standard that it's an enhancement for any other codec. It's an enhancement in the sense that it does provide compression efficiency and in video delivering workflows today. But it's also low complexity, meaning that it uses highly optimized tools that can be deployed on existing architectures, on existing silicon, as a software upgrade, if you want. So how is this possible? How does LCEVC actually works? Well, LCEVC is an enhancement layer. So it works by taking a lower resolution picture that is encoded with your base codec, a codec of your choice. It could be, as I said, AVC, HEVC, AV1, right? But it's used at the lower resolution. This means that the codec being used at the lower resolution for any operating point, you take a resolution and a bitrate of your choice, is working on an actually higher bits per pixel ratio. So it's largely working on a lower resolution, but more efficiently. The difference then between that lower resolution and the original is coded using different tools, using LCEVC, using 2 layers of enhancement, one that provides a correction of artifacts at the base resolution, a normative upscaler, so there is in the standards a number of upscalers that can be used to bring that lower resolution picture to the original or source resolution, at which then a second layer of enhancement is added. This layer of enhancement is typically constituted by high detailed information, high frequency information, the high quality elements, or the elements that make kind of the details and the high quality, the perceived high quality of a picture. So LCEVC is quite effective in coding this residual information with a limited number of tools, which makes it low complexity. And when I say a limited number of tools, the tools, if you go and look at the standard that are used by LCEVC to encode this information, is a dozen, compared to, you know, the hundreds of tools there are in HEVC or VVC. So these tools are particularly effective to encode this type of information. So again, what does this residual layer of data look like once you take away the reconstructed image by a base codec? Again, as I said, could be anything, AVC, HEVC, or VVC. The better the base codec, the kind of different at least this sub-layer of enhancement residual data will look like. But, you know, once you take away from the source that reconstructed picture and upscaled picture, this is the type of information that you see left. And it's sparse information, it's high detailed information, it's high frequencies that is difficult to infer with an upsampler, even a super resolution upsampler. And so this information is what's coded by a LCEVC enhancement layer. So currently, LCEVC, as I said, is going through MPEG ratification. It's gone through the various stages from the call for proposal that was issued in October 2018, through a number of iterations in the working groups. It's been through a first round of first ballot with the ICE organization in October last year, and it's currently in ballot with the ICE organizations to reach its final draft international standard status, which, all things going well, should be achieved by the next plenary at MPEG, which is in a few weeks' time. In parallel to the specification of the elementary stream for LCEVC, additional work streams related to LCEVC are ongoing, including its mapping into various container formats like MPEG2 transport stream and ISO BMFF, as well as an additional work stream for conformance and the definition of a reference software specification. So in terms of performance, I mean, we could spend a lot of time here, but I will refer you to probably a couple of sources a couple of references that you will find on the web and you can analyze more in detail. But kind of the performance of LCEVC across a different number of operating points, resolutions, applications, and different bases has been the subject of studies by MPEG and other consultants, associations, and universities outside of MPEG. Here there are a couple of papers, one from the ITU and one from an analyst, Jan Ozer of Streaming Media. The data kind of highlights how LCEVC provides benefits, both in this case on top of JM and HM, which are the reference models for H.264 and HEVC. These are tests that were conducted within MPEG and showcase the increased performance from a computational perspective of a stream that is being enhanced with LCEVC. Performance varies and is important to notice depending on the metric that is being utilized, whether it's PSNR, VMAF, or as they do in MPEG, focus on the mean opinion score, so on the subjective evaluation of a stream. So depending on the metric of choice, benefits, in this case with the reference model, will vary between 35 and 45% for 264, and from 9 to again 40% with HEVC. Again, these are test model results. Similar behavior and similar performance gains we'll see with the application of LCEVC on real-life implementations of these standards. In this case, we've done some experiments, and I give you just an example on top of X264, open source implementation of H264. Again, we see benefits ranging in the 40 to 45% gain in terms of bandwidth requirements. Very recently, actually, I ran some experiments on 8K picture using HEVC as a base. And again, there I see 40 to 50% gains depending on the operating point on top of using HEVC on its own. And in this case, it was X265 running with medium presets, to the point that it brings, in this case, very extreme, but it brings 8K down to a level where it's kind of feasible on networks and bandwidths that are available to people's houses actually today. As I said, it's not only about the compression performance, it's about the computational performance as well. And the low complexity means that it can run faster, and we see typically gains in the order of 2.5, 3, sometimes even 4x compared to the base used on its own in encoding. Again, how is this possible? It's possible because the base is used at the lower resolution, so much lower computational intensity for the 265 or 264 or AV1 in this case 265. And the tools of LCEVC are very light, as I said, very non-numerous in number, but also designed to target the architectures that are available in compute today. So it's very amenable to parallelization, and therefore GPU implementation or SIMD code for CPUs. On the other side, on the decode, again, these are some of the tests that were done independently, show that LCEVC can actually reduce at a given operating point the power required by the decoder. Again, a combination of smaller images for the base and a low complexity enhancement, or if you compare it to the same bit rate, kind of consume more or less the same power as what's available in hardware today. I talked a lot about 264 and 265 because those are codecs that are available today, and one of the unique selling points, if you want, or one of the uniqueness of LCEVC is that it's deployable today as a software retrofit on existing platforms, whether it's mobile or not consumer devices. But its benefit expands to future codecs as well. And this is an extract, again, of a paper that was presented at the SPIE conference, where the university in Italy showed that the benefits of LCEVC are applicable to next generation codecs like VVC, bringing, in this case, 7 to 10% performance gain from a compression perspective, but up to 4x the computational gains. So where is LCEVC applicable? Well, better compression is obviously applicable in many applications, from higher quality delivery of kind of live sports to immersive experiences e-gaming, etc. We are currently involved in a number of different projects and deployments, and this is possible again because LCEVC doesn't have to wait for those kind of cycles of deployments that are typical of previous generation or existing generation of compression as well. So it doesn't have to be hardened in silicon at the encoder or the decoder. So today we're working with a number of different operators, service providers to enhance a national catch-up service to deliver kind of higher quality with a major sports OTT provider. We're working with an esports streamer where actually we can provide 1080p 60, a larger number of users that are actually largely browser-based. And again, LCEVC doesn't have to be supported natively by the browser because it can be decoded using WebGL WebAssembly, which is supported by 99% of browsers that are out there today. Again, VR, we're involved in a project where LCEVC can allow on existing VR sets, on existing chipsets, basically higher resolution decode, higher than what's supported natively by the chipset itself. And another application is Web News Portal, where we're providing full HD kind of news across all of their different properties, all of the different platforms. Again, it's not just Vinnova currently talking about LCEVC. As I said, Jan Ozer did a lot of experiments, and his report is available on his blog for everybody to look. People like the news association Al Jazeera, Mediaset, the Italian broadcaster, have been vocal about their support of LCEVC and what it can bring to their services. So what do we do as Vinnova? Just to wrap it up, as I said, we've contributed to LCEVC as a standard, but we're also, while we were tracking its development, we've been working on an SDK, so on a set of libraries across all of the different platforms in encoding and decoding, because we believe that LCEVC can have a true impact on services, but can have a true impact today. So as it reaches standardization, we will be ready with a generally available version of an LCEVC SDK that can be used to deploy LCEVC across all different applications. And here is just a map of what we do and what we have. Again, we develop an SDK for encoding and decoding across all different platforms and architectures, from x86, ARMs for mobile, GPUs, and even FPGAs for cloud deployments, for example. And on the decoding side, we have already the full stack that goes from IP ready for SoCs, and we are talking to a number of different device manufacturers, all the way to a scripted version that can be run in purely as a scripted function within a web player in a browser. We make these SDK available with a number of different reference integrations. So today we have an early access program where people can access these libraries within an FFmpeg enabled for LCEVC. Or on the player side, again, most of the most popular projects out there, we have patches for to enable them with LCEVC, and we make these reference integration available as as a starting point or as an example for people to build into their application. So just as a reminder, again, it's why is LCEVC different? Why should I notice it? Why should I try it? It's it's a standard. Again, it's the only enhancement standard out there that can enhance any codec, any existing or future codec. It provides compression benefits, and it's low complexity, meaning that it can be deployed in software today. More information, please do get in touch. ping me or write to info@binova.com. But more than anything, please do go on lcevc.com. If you click on resources, you'll find a lot of kind of presentations and a lot of the tests and the papers that I refer to, both the ones from the universities, the ITUs, and also if you want to have a look at kind of some performance figures on LCEVC. And you probably find a good explanation of how it works as well. So hopefully this gave you a bit of a introduction to LCEVC. Again, I don't know how much time I have left. I lost a little bit track, but I'm happy to take any questions.
No, I think we have 5 minutes, Fabio. Thanks for that wonderful presentation. Very cool introduction to LCEVC, the coding standard for us. So anyone have any questions? Or probably let me start. I know that you presented results on AVC and HEVC as base codecs. What happens tomorrow if somebody wants to try AV1 or VVC? How does it impact the decoder and the the client-side implementations? Does the enhancement layer remain the same, or is it a completely different implementation each time a new base codec is used?
Thank you very much. Very good question. So LCEVC itself is base codec agnostic. Right? It receives a reconstructed picture and it encodes as efficiently as it can the difference between that and the source. So it can be equally applied to VVC or AV1. And in fact, the results that I showed from the SPIE paper that were related to VVC were kind of derived exactly like that, just by running the VVC reference encoder and then applying LCEVC blindly, if you want, on top. When it comes to real life implementation, of course, the way that the bit rate, for example, is allocated between the two different levels and the decisions that are taken on a frame by frame basis affect the overall performance of the combination of the two. So while we run a lot of tests in the lab to kind of isolate the behavior with the test models, we encourage people to kind of look at the real life and take our FFmpeg implementation and run it with X264, X265, or AV1. So we currently support about 20 different base codecs or base codec implementations that I said range from the open source to some of the proprietary ones like MPEG by NVIDIA or QSV by Intel, and so on and so forth. Currently, there is not yet a VVC implementation that we can develop a kind of plugin for. But as soon as that becomes available, it's easily added to the suite of base codecs that we support. AV1 in its libeom kind of version is already supported, so it can be tested.
Thank you. Thanks for that. Anyone else have questions?
I was obviously very clear in my presentation.
Yes. So should we switch over, or let me just wait? I'm just checking on Slack, the video dev channel. I think Scott had a question. Are there client-side libraries? You answered that part. No, there's nothing on the...
Yeah, on the client side, if you let me, actually, I'll elaborate just a second on that, because on the encoder side, as we said, we took an approach where we kind of optimized LCEVC, and then we have a plug-in architecture where different encoders, different base encoders can be easily plugged in. Literally, is a matter of days to add an existing or an existing different base encoder. On the decoder side, a lot of people are asking me, oh, how are you running that base? But again, we try to kind of separate the LCEVC and the base codec by leveraging the capabilities of the devices already out there. So the implementation is fairly modular, whereby we use whatever decode capabilities are already on the device. So whether it's a mobile phone, whether it's a browser, whether it's a set-top box, we use typically hardware decoding or native decoding for the base. And then the load of LCEVC is spread across the remaining compute power available. And this is how, for example, even on a mobile phone, we can run with lower power consumption than native itself, or the same power consumption at the worst case, because we leverage the hardware that is already available on the device.
Fantastic. Scott, I hope that answered your question. If not, you can ask a clarification and I'll be the relay. So just another general question from me, Fabio. So suppose, I mean, once the standard gets ratified, rate control is never usually a part of the standard. So yeah, do you have any recommendations or from your experience on how much should be allocated to the enhancement and how much goes to the base?
It's a very good question. And actually, when we started kind of experimenting, we had a rate control algorithm that, depending on the operating points, tried to kind of split the bit rates allocated to base versus the enhancement in a fixed manner. So we were experimenting with like 80-20, 60-40, 70-30, and that's possible. And typically, you will see it still depends. On average, you can take across the stream, you maybe see, I don't know, 20% of an enhancement. However, as we analyzed the behavior, the rate control got a lot more sophisticated. And if you think about it, a base codec can be more or less efficient depending on the complexity of the picture. And I think the next talk will largely address this, right? Video is not a constant and it will vary in its complexity. And you can kind of modulate that to achieve a constant quality for the base, for example. So if we set the base to reach a constant quality factor, then we will see that bitrate of the base modulating a lot, and the bitrate that we have available for the enhancement also varying literally on a frame by frame basis, to the point now that we can achieve a lot better compression efficiency really by modulating how the bitrate is allocated. If you can imagine, again, a static scene or a scene with a lot of detail can be very effective for the base, using motion estimation, for example, and we can save a lot of bits to encode those high frequencies with enhancement. When a scene is software, there's a lot of movement, maybe you want to spend a lot of the bit rates, a lot of the bits on the base to get the most out of your motion vectors, for example.
Yeah.
So I don't know if that answers your question, because it's not a fixed number, but you know, it's part of what makes the implementation, or what will differentiate different implementations of LCEVC is very much how you juggle the fact that you have two different algorithms that behave in different ways.
That makes a lot of sense, actually. And I think that's almost a perfect segue to our next talk. So if there aren't any other questions, I thank you on behalf of everyone, Fabio, for this wonderful presentation. And like
well, thank you very much
for
giving me the chance to present it. Thank you.
Thank you. So as Fabio mentioned, no two videos are the same unless it's the same video. And that's why the whole revolution of content-aware encoding, per-title encoding is there today. Our next speaker, Saravanan Silvarajoo, is an architect at Bitmovin, and he's going to present a talk titled per title, the fundamentals of per title encoding. So over to you, Saravanan.
Hi, thanks, Krishna. Let me just share my screen. Give me a sec. And here goes. So yeah, I'm sharing my screen now, and
yeah, we can
turn on. Cool. Let me turn on my video. Let me see that. Turn it on. Okay. Cool. Yep. So, hello everybody. Thanks, Krishna. Thanks, Invid, for this opportunity. So, a quick intro. Like Krishna mentioned, I'm Saravanan from Bitmovin. I'm based in Singapore. Solution architect for the APAC region. I help customers integrate with Bitmovin products. And in today's presentation, I'm going to touch on per title encoding. It's a more conceptual presentation than a technical one. I'm not going to go into the codes. I'm not going to go into algorithms and how it's done, but a more conceptual one. And as you can see in the presentation, the tagline is delivering better quality at lower cost. So that's one of the objectives of per title encoding, right? So I'll start. Right. Actually, before I start, this deck is reference of one of our blog posts, one of Bitmovin's blog posts. This is the link. Materials from this site. From this slide, I took it from this blog post. And if you want the full details, you can go and read this blog post. And because most of us are engineers, we learn best by dismantling the bits and bytes. And in this link, there are some examples, so that and you can even try the per title encoding from that link there. Right, going on, next slide. So agenda. So what am I going to talk about today? 3 things, maybe 4 things here. 3 things. First thing, I'm going to give a bit of an introduction, more of a history lesson on per title, how it evolved. Then we go into a 5,000-foot view on what per title is. So we look from the top, understand the objective, how it is done. Again, a very quick overview, and then appreciate the results of it. And once we have that understanding, we go in a bit deeper, see what happens under the hoods. But then again, the trick about per title is the secret sauce, right? So Bitmovin has its patents in this technology, and then I'll try to touch on topics where so that people can develop their own secret sauce for per title and rock the evolution of per title. And we'll have Q&A, and then we'll wrap up. Cool. Introduction. We start with the history lesson. So per title encoding, it's not a new concept. It's been there since 2012. And there are research papers online that date back to those years, and some of them, or many of them, are from Bitmovin's co-founders. And since then, a lot of things have leapfrogged, right? There's been cheaper yet more powerful compute. There are algorithms to subjectively and objectively compute the quality of the content. So code can now tell how good the content is, just like how our eyes tell, right? So this has helped per title substantially. And also, why per title has gained much traction is because this can be applied in the encoding process. And as we can see in the presentation later, it only tunes the bitrate ladder. It does not require a change downstream, like the packaging, DRM packaging at the CDN side. On the player side, it does not require changes, right? So that's why this technology can be quite effective to reduce the bits required when we encode the content. And in the last part, so I guess that's why I call it the lower or lowest hanging fruit. And the last line is amortizing the benefits downstream. So when you save on the bits and bytes when you're encoding, when you deliver this bits and bytes to the customers, to the end devices, so that's when you save. And that's the part where your service scales, and that's where you can save it most. And I heard from the top that Netflix, even if they can get a 1 to 2% savings in encoding, they will re-encode the entire catalog, because that's how huge their scale is. And then if you think in terms of bits that are being delivered, it's going to substantially save them in terms of cost, right? Moving on. So what is it basically? So I'm going to have a quick overview, a macroscopic view of what per title is. So here, So the objective of this picture, right, is number one, yeah, we all miss the seas, the beaches because of COVID, but that's not what this picture is there for. It's to show that a content, different titles can have different types of scenes in it. So the one you see on the left is an action scene. There's a lot of movement in it, whereas the one on the right, it's a very static scene, akin to a documentary, versus the one on the left, which is a more motion scene. Hence, having a fixed bitrate ladder is not going to be a fair. It's kind of a brute force method to encode both of this content, right? The objective, the goal of per title is to select a bit rate, right, such that there's just enough bits to capture the content and to present it in a perfect viewing experience. Not more, just enough so that our eyes can enjoy it, right? Anything beyond that perfect viewing experience is stripped out. As we will see later, more bits can increase the quality, but our eyes can't appreciate that. So that's the objective of per title. And fundamentally, what is it? What happens is you encode the same content with different bit rates. So you do multiple, you encode the same content with different bit rates, and then you compute the quality metric to convert to kind of predict the convex hull. And from the convex hull, then you pick out the bit rate that's best or most suits that content, right? And quality metric, it does not, in this slide I've mentioned PSNR, but it doesn't need to be PSNR. We use a few different, we use VMAF, we use same, and we have our own in-house metrics as well. But the objective here is to see how efficient that bitrate is at to pick the most efficient bitrate, yet still keeping the quality. And so there's a fact snippet there on the slide, you can see. So this is what I was referring to earlier. With regards to the PSNR quality metrics, once your quality, or once the numerical value is above 45 dB in comparison with the mezzanine content, our eyes can't perceive the content, can't perceive the difference, right? So no matter how many bits I throw on it and increase the PSNR value, the quality, the numerical value, our eyes are not going to be able to appreciate that. The next slide shows that in terms of a diagram, right? So you can see the blue line here is a standard profile. It's your fixed bitrate ladder. It's not uncommon to see 7 or 8 renditions in a fixed bitrate ladder. And the orange one is a per title generated bitrate ladder, right? And you can see that from I'm gonna just enable my pointer. So you can see that from there is a lot of cost savings in the top, in the highest quality profile. You can see that using per title, you're able to generate a bitrate that serves a quality of above 45 PSNR, whereas using a standard bitrate ladder, you get a quality of more than 45 at 70, using a much higher bitrate, close to 4 Mbps, right? And above this line here, if you recall the fact that we discussed a bit earlier, you notice above this line, there's no visible quality improvement. So essentially, we have saved close to 3 Mbps worth of bits that are saved for one person for this piece of content to one device, right? So that's a lot of savings. That's one. And another thing is we've also improved the quality. So at the bitrate of 200 kbps, we have upped the quality to above 35 decibels PSNR value. Whereas in a fixed bitrate ladder, it's sub 30, right? Close to 25 decibels. So we have done two things. We have reduced cost, yet maintaining the quality. And we have also improved quality at an existing bitrate, right? So now that we have covered the macroscopic view, I'm going to go into a little bit more detail on the per title logic and workflow. Yeah, so this is the overview of per title. On the left we have the fixed bitrate workflow. On the right we have the per title workflow. In the fixed bitrate workflow, it's pretty straightforward. You give it a ladder, then you encode it, and it's outputted. The ABR content is output and stored in the storage CDN. On the right side is per title. If you recall, earlier we mentioned that in the history lesson, we discussed the fact that per title is the lowest hanging fruit because this is only this part of the workflow changes. Nothing on top, nothing below is required to change. So only this part of the workflow changes, where first you analyze the complexity of the video, you predict the convex hull, then you dynamically generate the bitrate ladder, and you pass it down to encoding. So from this point onwards, you basically encode it with the new set or this specific set of renditions, and then you store it. So yeah, so that's what it is. And when so I'm gonna explain on the first thing that happens, the first extra bit or the first magic that happens as part of per title, where you analyze the complexity. A huge part of the secret sauce here is to estimate the complexity efficiently and as accurately as possible, right? So different titles can have different types of content in it, scenes in it. You can have an action scene, you can have a slow-moving scene, you can have very beautiful picturesque scenes in it. And to estimate that complexity is the challenge. As a matter of fact, there are some movies where it has a mix of all. So how are you then going to estimate the complexity of the scene? And that too, you have to do it fast. You can't take too long to do it at encode time. And one of the ways that we've done is to use the CRF, the constant rate factor from the H.264 codec. And in CRF, at a lower CRF value will typically output a higher bit rate. It indicates that I want a higher quality. And at a higher CRF value, you're indicating I want a lower quality, so it's typically a lower bit rate, right? And in this diagram here, the top left-hand corner, Big Bucks Bunny, it's a cartoon content. So you can see that within at the highest quality versus the lowest quality, the curve gradient, it kind of indicates that, hey, it's not too much of a difference. It's a first gauge of complexity, how complex that content is. So you probably, when you recall earlier in the overview, you encode it at different bit rates at different CRFs, and then you see different bit rates. You first then use that to understand how complex this content is. But of course, it's not as simple as that, right? So at real time, you can't be encoding the entire content in different CRFs. The algorithm either needs to be able to decide which portions of the content to do that, and then you use that to compute, or you parallelize the entire encode, and then you combine it back. And it's got to be fast, it's got to be cost efficient at the same time. So the trick of per title, you recall per title has been there since 2012. So the trick actually is to make it commercially viable, so that it's fast, cost efficient, and so that it's commercially viable. And that's where all the optimization comes in. In the next slide, we are going to the next part. So once you have understood, or once the algorithm, or once the code has understood how complex the content is, once we have computed the complexity factor, then now we go ahead and predict the bit rates and resolution. And this is done using the convex hull. And how we typically do it, or how it's done, is we break up the content into three different sections, or three different buckets: low resolution, mid, and high. And for each we break it up into different, we re-encode it in different bit rates, and select and plot a hull for each bucket, and then pick the bit rate at the peak. Pick the bit rate at the peak. Well, it's tongue twister really. You have to pick the bit rate at the peak to know, and then use that and then use that for your encoding ladder, as your bit rate ladder. And again, the magic here is, how are you going to determine these different bit rates? You can't randomly decide on bit rates and then transcode, re-encode them and get a quality metric, and then use that as feedback and re-encode in a different bit rate. You can't do that. So and one of the magic that we have used is to use the complexity factor, metrics from the complexity factor, input it into a machine learning model, and then use that to predict the resolution as well as bit rates. Yeah. And to determine the convex hull, and then pick one of the bit rates for the ladder, for the bit rate ladder. Next, this slide, what it aims to do, or what I hope to talk on this slide is, so once your bitrate ladder is selected, so you will have a new ladder, something like this, that is with bitrate automatic with this numerical value automatically calculated, and sometimes you can even possibly look at changing the resolution, right? Why I wanted this slide is to talk about how a low complexity content will vary from a high complexity content. So in a low complexity content, typically a per title algorithm, what it does is that it will reduce the bit rate, keeping the quality at the same, right? It doesn't touch the bit rates, the lowest bit rates that much. In contrast, for a high complexity content, it touches the low bit rates, and it increases the bit rates for the lower resolution, and in so doing, it increases the quality. It's like a little bit like Robin Hood. So it takes the bits from where it's not needed, and it gives the bits to where it is needed, right? Improving quality, and then improving quality here, reducing cost here. And these are results that we have seen from using per title, right? So this is a low complexity content, and this is a high complexity content. I've highlighted the two different rows that we can talk about. So the top row over here is a low complexity content, a cartoon content. We have reduced the bandwidth for the highest resolution. You can see that the bit rates that are required, we have reduced it from this to this, and we have saved about 30% in terms of bits. And there is a substantial drop in PSNR, in quality. But then again, if you recall what we discussed earlier about quality, once it's at above 45 decibels, your eyes really can't perceive the difference. So hence, even though there's a quality drop from a numerical perspective, from a real life perspective of the consumer's eyes, they're not going to be able to catch that. So to the consumer, we're still delivering an equal quality content with lesser bits. So that's cost savings over here. In the bottom table here, this is a high complexity content. It's action content. And what we have done here is for the lowest resolution, we have increased the bits. We have increased the bits by 50%. And what we have also done is that we have also increased the quality of this content. So we've taken the bits from here. In a way, we've taken the bits from here and given it to this content. So we've increased the bits and given a better viewing quality. And by better viewing quality, I mean perceivable by the human eye. Right?